This is the solution to chapter 17 video assignment 1. There's 3 separate questions. I'll go through them one by one. But it first gives us a table for some reduction half reactions and their corresponding reduction potentials. So I wrote those up there on the board. The first question says, which substance is the strongest reducing agent and which substance is the strongest oxidizing agent? Consider all substances, both reactants and products. So a reducing agent is something that causes another substance to be reduced. So it itself becomes oxidized. And an oxidizing agent causes something to be oxidized, so it itself is reduced. So the strongest reducing agent is going to be the substance with the strongest oxidization potential. And so we're going to find everything for this problem in the first one here because it's got the largest magnitude number. This is the reduction potential, right? So it's going to get reduced the easiest. So this will be the strongest oxidizing agent. So the strongest oxidizing agent is this A3+. Now, by the same token, if you were to switch this equation around, so it was A plus going to A3 plus 2 electrons, this value would be negative 1.47 for the reduction potential. So it's going to give up electrons very readily. It's going to be oxidized very easily. So it's going to be the strongest reducing agent. So the strongest reducing agent is going to be this A plus because it's going to have the largest magnitude oxidization potential so that it gets oxidized easily and reduces something easier. So there's your strongest reducing agent and there's your strongest oxidizing agent, all found within that first equation there. Question 2 states, or asks, which substances can be spontaneously oxidized by B2+ and which can be spontaneously reduced by C+? So spontaneously oxidized by B2+. So if they're being oxidized, that means B2+ is being reduced. So what we can do is we can look at B2+'s reduction potential, and everything that has a lower reduction potential than that is going to have its electron taken and B2+ is going to get it. If that makes sense, since this is a 0.6 reduction potential, that's how much pull it's giving out electrons. So anything with a weaker pull is going to be oxidized by B2+. So those are going to be A2+, right? Because if we switch it, this will be negative 1.47 for the reduction potential. So A+, it'll be, well, I guess B also, but it'll be, sorry, where was I? It'll be C2+ because that's negative 0.21, and it will also be D because that's negative 1.38. So because these are a lesser magnitude than this is going to take electrons from them, and if we swap this one, the A+ is going to be negative 1.47 reduction potential, so the B2+ is going to take electrons from it. Yeah, so that's going to be all of the things that can be spontaneously oxidized by B2+. Now, spontaneously reduced by C+ is the second half of this question. So we're just going to look at this one here, but we'll flip it. So C+ is going to have a reduction potential of 0.21 positive, right? Because if we swap it, we have to switch this. So C+'s reduction potential is going to be 0.21. So everything that's going to be spontaneously reduced by C+ means it's going to be giving electrons to that, right? So everything with a stronger reduction potential, a greater magnitude reduction potential than 0.21 is going to be spontaneously reduced by C+, because it will be stronger, have a stronger pull of electrons than C+ does. So it will be getting oxidized and it will be reducing the other thing. So those values are going to be A+, right? Much larger than 0.21. It's going to be B2+, much larger than 0.21. And if we swap this, D-, it's going to have a reduction potential of 1.38 positive. So those are your things that will be spontaneously reduced by C+. Okay, now question 3, or part 3 of question 1, whatever, video question 1. Write the balanced equation for the overall reaction that delivers the highest voltage, and calculate E for that reaction. Sorry. So if we just look at the 2 highest magnitudes of here, we have A3+, which is a very strong reducing agent here, and you've got the D plus E minus, D is a strong oxidizing agent. So if we combine those two, we have the half reaction for D here, D plus electron equals D minus, and we can swap the orientation of that. So it'll be D minus is oxidized to D plus E, right? Because we're going to need an anode and a cathode. So one has to be the reducing agent, one has to be the oxidizing agent. So we got to flop the direction of this one. So this is going to be oxidized to this, whereas this is going to be reduced. And then, since there's only one electron involved in this half fraction, there's two in this half fraction, we have to multiply this whole thing by 2. So we'll have 2D minus, it goes to 2D plus 2 electrons. And we have the A3 plus 2 electrons goes to A plus. So if we just sum these two half reactions, we can have the whole cell here. So it'll be A3 plus 2 electrons plus 2D minus goes to A plus 2D plus 2 electrons. And our electrons are going to cancel there, so we know that this works. So here's our final reaction. A3 plus 2D minus reacts to form A plus and A plus 2D. Now, the equation to determine the E for this cell is the reduction potential of the cathode minus reduction potential of the anode, or the reduction potential of the cathode plus the oxidation potential of the anode. So the reduction potential of the cathode, the thing that gets reduced, is our A, so that'll be 1.47 volts, minus the reduction potential of the anode, or if we just swapped it, the oxidation potential would be 1.38, okay, so that becomes a plus. So it's the 1.47 volts minus negative 1.38 volts equals 2.85 volts is the value is the voltage of this galvanic cell, this voltaic cell.